Hi, so thanks for the introduction. And thank you all for being here. I know the black hole talk is on in the other room, so I'm very pleased that some people turned out for this one. And so I'm going to be talking a little bit about sample efficient learning of phases of matter, which is a merger of two papers, both of which have these good looking authors down here at the bottom. So it's a merge talk, so I'm going to have to go pretty fast. But I'm going to start with some motivation and talk about what it means to learn a phase of matter and why you should care about it, before talking a little bit about thermal phases of matter and learning more general phases of matter. And then if I have time, I'm going to shoehorn in some results about Gibbs state tomography. Okay, so suppose I have n interacting spins on some interaction graph, like this one given here, and they have some local Hamiltonian defined over that graph. And we know that if this comes to thermal equilibrium at some inverse temperature beta, it's going to be in its Gibbs state given by the exponential of the Hamiltonian given up here. And there are a bunch of things that we might want to learn about this Gibbs state. In particular, what are its local expectation values, its entropies, its correlation functions, fidelities, etc. These are tasks that you see in condensed matter physics, but also in things like machine learning for Gibbs sampling. So this is a task that we're interested in. And the question is, how hard is it to, or can we efficiently compute these tasks? So a kind of very obvious thing you might try and do is, I give you this description of this Hamiltonian and these interacting spins. You go away and you try and compute some kind of approximation to your Gibbs state, which approximate, let's say, the local observables to your Gibbs state to high precision. And the question you can ask is, how easy is it to do this? Well, we know at infinite temperature, or beta equal to 0, this is a trivial task. It's just the maximally mixed state. And it turns out, actually, that at high temperature, we often have very efficient or polytime algorithms that compute local observables and do other tasks at these high temperatures. On the other hand, if we go to 0 temperature, or beta goes to infinity, we end up with the Gibbs state being the ground state. And we know that predicting properties of ground states is QMA hard. And then, sometimes you might ask, what's the complexity of doing this in somewhere in the middle? And it turns out that many of these kind of high temperature algorithms break down at some critical temperature, beyond which approximating things like local observables becomes QXC hard, which is a complexity class that people are going to talk about tomorrow in one of the talks. So in general, up to computational assumptions, computing properties of Gibbs states is going to be an exponentially hard task. This is a bit of a doozy because it's something we'd really like to be able to do, even on a quantum computer. So given that we can't efficiently learn properties of Gibbs states from just a first principles description of our Hamiltonian, can we kind of cheat? Can we use information from other states to learn properties about our particular state, our particular Gibbs state of interest? In particular, this is kind of the question, can learning algorithms solve challenging many-body physics problems faster or better than non-learning algorithms? So the situation that we're going to be in is going to be something kind of like the following. I'm going to have a Hamiltonian, and it's going to be parameterized by a bunch of parameters, let's say m parameters. And this is, some sort of like configuration space of parameters or something like that. And we know that for each point in this parameter space, there's going to be a corresponding Gibbs state just kind of mapping down. And the task I'm going to be interested in is I'm going to give you a bunch of samples, these y1, 2, 3, 4, or however many samples you want. And I want you to predict, predict or learn local expectation values of local observables everywhere else in the parameter space that you haven't seen previously. And ideally, I only want you to do this with access to a classical computer and measurements on these states. So the task is given a local observable and a parameter x, or a point in parameter space. Use classical data collected previously to predict the local observable to high probability. Now, you might very well turn to me and you go, James, this is actually a kind of, it's not clear why this should be possible. In particular, if I give you 2 points in parameter space, it's not clear that they're going to have any relation to each other in any meaningful sense. In particular, even if I have a very nicely smoothly parameterized Hamiltonian, if I take 2 points either side of a phase transition, these states can have very different properties and may not be related to each other in any way. So what we're going to do is we're going to impose an additional promise on the problem that we're going to be interested in. We're going to promise that the states I give you, or these samples I give you, all come from the same phase of matter, so like an Ising ordered phase or something like that. And all the samples that I give you are going to come from the same phase of matter, but also the point I'm going to ask you to predict is also going to come from the same phase of matter. And if this isn't true, if we don't enforce this promise, in general, this task is going to be much, much harder. So the problem we're going to consider kind of maybe more formally is the setup is I'm going to have a parameterized Hamiltonian, parameterized by, let's say, parameters in the region 1 to -1. And I'm going to give you access to Gibbs states and allow you to do measurements on n Gibbs states. And then I'm going to input, or I'm going to give you a point in the parameter space and a local observable. I want you to estimate local observable, right, or estimate this local observable to high precision. And the requirement that this data is taken before the local observable and the Hamiltonian of interest are chosen gives this kind of a broader applicability, right? It means you can't make adaptive measurements based on the point in parameter space and the point in parameter space and the local observable given to you. And this data, I've kind of like talked about samples of quantum states, but it could come from anything really. Lab data, it could come from Monte Carlo simulations, tensor network simulations, anything that gives you a reasonable estimate to local observables. And the idea of this task is to give you access to points in parameter space that you can kind of extrapolate to when taking samples is an expensive task. But we're not the first people to consider this, actually. A task like this has kind of been considered before. Robert Hong and collaborators did something kind of similar, but not for Gibbs states, but for gapped ground states. So very briefly, they consider the case where you have a parameterized Hamiltonian, and rather than learning properties of Gibbs states, you now want to learn the properties of ground states. And they enforce the condition that their Hamiltonian is gapped everywhere in the parameter space, which, which corresponds to requiring that everything is in the same quantum phase of matter. So given n samples of the ground state distributed by the uniform distribution, they come up with a really nice algorithm, which basically does a kind of like a classical shadows or a classical measurement routine, does some kind of like classical machine learning magic, comes out on the other side and comes up with an estimator that predicts local observables. And it's really nice, it's pretty simple. Unfortunately, it has a sample complexity that scales polynomially in the system size and exponentially in the precision. And this is fine, but it's not ideal. It's still pretty expensive. The question is, can we go beyond this ground state learning to Gibbs states, and can we improve on this sample complexity to get something which is much more efficient? Okay, the answer is obviously going to be yes, because I wouldn't be on stage otherwise. So we're going to consider a similar situation. We're going to consider the case where, again, we have a locally parameterized Hamiltonian. You can consider our Hamiltonian as being a sum of local terms parameterized by parameters x. And I'm going to enforce the condition that everywhere in this parameter space, our Hamiltonian is going to have exponentially decaying correlations. So if I take two local observables, I consider the covariance between them, it's got to decay exponentially with distance. Now the reason I'm enforcing this condition is related to this phase condition, or the fact that we're drawing our samples from the same phase of matter. We know that if we have exponentially decaying correlations everywhere, then we're guaranteed not to have a second order phase transition anywhere in this region. So this is really enforcing the condition that there are no phase transitions in this parameter space. And our main result, or the first main result that I'm going to show you today, or tell you today, is that under this condition, this exponentially decaying correlations, we get, or rather, we only need logarithmically many samples in the system size and quasi-polynomially many samples in the precision, drawn from a sufficiently anti-concentrated distribution to construct a good estimator for local observables everywhere in the phase. Okay. So I'm going to try and give you a flavor of the algorithm. Unfortunately, I don't have too much time to explain the main proof. But the training stage is pretty simple. It's very similar to the Robert Hong result. So the idea is I'm going to give you your n samples on, let's say, some sort of lattice. And you're basically going to do a classical shadows routine. I'm going to give you these samples. And on each qubit, you're going to do a randomized Pauli, or implement a randomized Pauli. And then you're just going to measure each qubit and record the outcome, as well as the parameter that it came from in the parameter space. So this is basically a single qubit, a single measurement classical shadow routine. Okay, so now we've done the training stage. We now want to use this to make estimations or make predictions. So at this point, I give you the local observable I want you to measure or find an estimate of, and I give you the the point in parameter space, or the Hamiltonian, that I want you to predict Gibbs properties of. So I give you this, let's say, local observable O at this point in the lattice. And what you're going to do is you're going to draw a region around the support of this local observable. And the size of the region depends on the decay of correlations and other properties. And then basically what you do is you look at the Hamiltonian in this region, and you look at which parameters are contained within this region of the lattice. And you look at which samples you have are close in parameter space to the point they've asked you to approximate. And you gather up all those samples in some set, and you simply take an empirical average with those classical shadow estimators I mentioned on the previous page. Turns out this gives you a sufficiently good estimator. And the reason we can do this, we can localize this part of the lattice, is due to this exponential decay of correlations property plus Lee Robinson bounds. These two properties basically ensure that all the physics of this local observable O are localized to an entirely local property, or entirely a small part of your lattice around the local observable. Okay, so that's great and all. So we know that given a thermal phase of matter with exponentially decaying correlations, we can predict expectation values to high precision with this complexity, which very nicely beats the previous result from Robert Hong and collaborators for ground states. But Robert Hong and collaborators came along and they came up with a better algorithm that matches our complexity. So that's great. So now we have efficient learning of both ground states and thermal phases of matter, provided that they both have exponential decaying correlations. So that's fantastic, but it's also slightly unsatisfactory. What about other families of states, gap states of matter and thermal states of matter? These aren't the only kind of phases of matter that you might be interested in. We can talk about phases with algebraically decaying correlations. We can talk about mixed state topological phases, dynamical phases, etc. What can I say about these families of states? Is there anything we can learn about these? So we're going to investigate this question too, and go beyond these kind of definitions of phase of matter. But if I want to talk about these more complicated phases of matter, we need a kind of more general definition of phase. What does it mean to have a phase of matter? And this, it turns out, is actually quite a controversial question within the condensed matter community, and lots of people may not like the definition that I'm working with. But we're going to work with the definition from David Perez-Garcia and Andrei Koza from 2019. So Andrei Koza and David Perez-Garcia, they say that two states on n-qubits are in the same phase if there's a rapid Lambda-ian evolution which maps between the two states, such that these two equations are true. So that is, I can go from one state to another state in kind of like polylogarithmic amount of time if they're in the same phase. And I must be also able to go backwards. It's got a reflexive property to it. So you can imagine if you have, let's say, an Ising model, you can go between states in the ordered phase, or you can go between states in the disordered phase. It turns out you can also go from the ordered phase to the disordered phase, but you can't go from the disordered phase to the ordered phase. This may not be super intuitive to everybody here. I'm just going to state it and maybe provide some justification. So the idea is that if I can evolve between states in a polylogarithmic amount of time, I'm not generating any long-range correlations during that evolution. And so in some sense, my local observables that evolve, they're still kind of local in the new state. And in particular, this ensures that they have kind of nice, analytic, smoothly perturbed properties. So nothing kind of too ridiculous is happening under these evolutions. Okay, so accepting this phase, or this definition of a phase of matter, we need to be able to efficiently talk about states that exist in our phase of matter. Generally, a state requires an exponential number of parameters to specify, and that's not going to be good enough for our purposes. So we're going to do essentially the same thing we did in the Gibbs state case. We're going to parameterize it not by the Hamiltonian, but now by the Lambda-ian. So we're going to set some sort of reference state for a star, and I'm going to refer to states not by a Hamiltonian, but by which Lambda-ian they can evolve under to reach them from this reference state. This is going to allow us to efficiently refer to all states in the phase. So the question is, can we come up with a learning algorithm which applies to this very general definition of phase? The answer, conveniently for this talk, is yes. And the answer, conveniently for the timing on this talk, is it's pretty much exactly the same as the thermal state learning algorithm. You parameterize your Lambdadian, and then you apply basically the exactly same algorithm as for the thermal state case, with some modifications. So this gives us the second main result of this talk, which is that we can use logarithmically many samples in the system size and quasi-polynomially many samples in the precision to learn expectation values everywhere in the phase of matter, provided the samples are taken from a sufficiently anti-concentrated distribution. So it turns out that this Lambdadian phase of matter provably encompasses this gapped phase of matter that I talked about earlier. And so our results about these Lambdadian phases of matter subsume these previous results on gapped phases of matter. They also probably encompass results about learning Gibbs phases of matter, but there are some kind of controversial points about that that you can talk to me about after the talk. Okay, so I've got a couple of minutes left, so I'm going to just power through some results on Gibbs state tomography that my collaborators insisted that I include. So as a kind of shoehorned in result, we also thought about learning Gibbs states. In particular, if I give you multiple copies of a Gibbs state, can you come up with an estimate for the parameterization of the Gibbs state such that the extensive qualities of the corresponding Gibbs state are close to the true value? What I mean by extensive values is, can we predict or can we estimate the values of Lipschitz observables to high precision as well as just local observables? So a Lipschitz observable is an observable which satisfies this condition here. So morally, you can think about a Lipschitz observable being Lipschitz if I can integrate out a particular qubit or any qubit and the spectral norm doesn't change too much. So this includes a set of local observables, but also many important quasi-local observables. And importantly, if my estimate is good in all local observables, in all Lipschitz observables, it means the entropies of my estimate are close to the true entropies of the state. And so we came up with a algorithm which does exactly this. And you can show that for any unknown Gibbs state with exponentially decaying correlations, there exists an algorithm which provides a description of the parameters of the Hamiltonian such that rho of sigma x prime, or the Gibbs state, approximates all these Lipschitz observables well using only polylogarithmically many samples, provided one of these other three conditions holds. The Hamiltonian is commuting, it's at high temperature, or the uniform Markov property holds. And there's a talk earlier about this from Kohawa. And the proof of this is not straightforward, but at a high level, you use quantum belief propagation to show the continuity in the Wasserstein distance of order 1. And then you use a Hamiltonian learning algorithm from Anurag and friends. Okay, so in summary, learning phases of matter is the task of learning a local expectation value to high precision and high probability while minimizing the number of samples, using samples taken from the same phase. And for the task of learning thermal phases and for Lambdadian phases, we get a number of samples that scales logarithmically in the system size and quasi-polynomially in the precision, which is better than previous results. And for Gibbs state tomography, we show that there exists an algorithm which learns a parameterization of the Gibbs state, and which is close in all quasi-local observables and requires only polylogarithmically many samples. That's all I have to say. I'm going to leave you with some open questions, and these are QR codes to the two respective papers. Hey, Lexi.
So what happens near phase boundaries? Like as you come closer and closer, do you need to collect like more data, or it just doesn't work at all?
Yeah, you do have to collect more data. Basically, I didn't state it, but there's a dependence on the kind of like the gradient of the Hamiltonian or the Lambdadian and the states between it. So it blows up as you get closer and closer to the boundary. Hey.
Hello. Hi, I have two questions. Could shallow circuits, shallow shadows help you in any way to get a better scaling?
Shallow shadows?
Yes,
as in
doing shallow tomography, but with short depth circuits instead of just a layer of Paulis.
Yes. So I guess if you did that, you could. So our estimator here only works for local observables. If you're doing shallow circuits, I guess you'd get better estimates for things like entropies and stuff, or over larger regions. I think. But in terms of just predicting local observables, I don't think it changes the complexity or the sample complexity off the top of my head.
Yes, and also about the sample complexity.
Sure.
If I remember correctly, in the original classical shadow paper, the sample complexity of doing shadow with a layer of Pauli was scaled with a 3 to the number of qubits. And how do you get from that to a log n?
I thought it was 3 to the number of qubits in the locality of the local
Yeah, 3
observable.
three to the locality of the observable, yes.
Yeah. So here we're just assuming the k is constant. So local observable for k is equal to order 1.
But that,
so it's just absorbed into
that
the
would still be
prefactor.
there then. If
Sorry?
or like
Yeah. It would still be there again
Okay,
if you were to do
okay,
this,
then.
including that.
Thank you.
No, thanks for bringing that up.
So James, is the quasi-polynomial dependence in 1/epsilon, is that inherent, or is?
Yeah, that's a really good question. I think the answer is yes. I can't kind of rigorously justify this. The idea being that if I take a Hamiltonian and I assume some sort of like exponential decay or some correlations or some length scale, and you look at the number of parameters that describe the Hamiltonian in that region, it goes to something that's like 2 to the power of polylog of epsilon, 1/epsilon. So it seems like that always appears. And there might be some clever way of getting around it, but we tried a little bit and we couldn't get much out.